Okay, good morning. My name is Raul, and I'm from the Federal University of Minas Gerais. First of all, I have to thank very much the organizers, not only for the opportunity to give the talk, but for the financial support. Otherwise, I would not be here. And I'm going to talk about quantum interference of force. And this work was made with my colleague, Marina Seni, who's over there with the red hair, and my supervisor, Pablo Saldanha. So let us start with the definition of what is this quantum interference of force. So given a massive quantum object, we will show how the superposition of a positive force with a null force is going to that is acting upon the object will give rise to a negative momentum transfer to the object. And of course, we have to do some post-selection. So let's go piece by piece on this. So we are talking about force. And this is why we need a massive object. Otherwise, we cannot talk about force acting upon it. And we are going to do superposition of two different forces. And this is where interference will come in. And finally, the quantum comes in allowing us to having a negative momentum transfer in the end, in the sense that it's impossible to have a statistical mixture of a positive force and null force acting on an object, and in the end you get a negative momentum transfer. So we will need a quantum superposition of these two things in order to have this negative momentum transfer. And this is why we call this effect the quantum interference of force. And after, I'm going to show you how this effect can produce an effective electrostatic attraction between two electrons, and when they propagate through an interferometer, and of course when they are subjected to post-selection. Okay, so this is the overlook. We are, in fact, inspired by a very interesting paper by Aharonov and collaborators. A few years ago, they were investigating the classical limit of quantum optics. So they have this modified Mach-Zehnder interferometer, where if you send classical light into the interferometer, and you are looking at this mirror here. So they are treating this mirror quantum mechanically. It just means that they have to use a wave function to describe its motion. So they see that if you set up these angles properly and the transmission coefficients of the beam splitters, there is some situation in which this mirror will be pushed to the left, that is towards inside the interferometer. And the classical explanation for this, of course, is that the light that comes out on this way, so it comes to detector D1, it is giving more radiation pressure than the light that is inside the interferometer. So in this way, that is why classically the mirror is being pushed to the inside. On the other hand, if you go to the single photon description, there is a way, a clever way, that you can adjust this photon that comes here, gives a zero total momentum to the mirror. So in the end, if the mirror is pushed to the inside, it is the component of the photon that comes to this detector that is giving a net momentum to the mirror. So in the single photon case, we have to say that it is this photon that comes here and never pushed the mirror from the back that is pulling the mirror to the inside of the interferometer. But of course, it can only do nothing when it comes to this path, or it can push the mirror to the outside. So there is an interesting interference effect going on inside the interferometer here that is making the photon, causing the photon to pull the mirror to the inside. And the authors show this, but they use weak measurement formalism to do this. What does it mean? It means that the momentum kick that the photon gives to the mirror is very small when you compare it to the momentum uncertainty of the mirror. And what we are going to do, so we are going to generalize this we're going out of this quantum mirror thing and we go to a general quantum system. And we are also going out of the weak interaction regime. Why do we do this? Because then we will be able to propose a feasible experiment that could detect this strange effect of the anomalous momentum transfer to this quantum object, and due to what we call the quantum interference of force. Okay, so the first physical system that I want to show is an electron Mach Zehnder. I'm not going into the details of how you could build this now, but I'm going to show later. So imagine that you have an electron. It reaches this beam splitter, and it has transmission coefficient T to go to path A, and reflection coefficient R. And on path A, nothing happens to the electron in force-wise. And on path B, there is a capacitor that will give a momentum kick on this electron upwards. That is, there is a force acting on the electron, and it's going to get a momentum kick up. And after this second beam splitter, it's going to be a 50-50 beam splitter. These two things will be superposed in the two exits. So in the end, what we have on one exit, we have this original wave function. I didn't say that we are only going to be concerned with the vertical degrees of freedom. Nothing is going to happen in the plane of propagation. So from path A, we have this amplitude T, and nothing happens to the original wave function in the momentum space, and the coefficient R, given the amplitude from path B, and the wave function gets displaced because of the force. This phase here is just, you can set with the mirror positions and stuff like this. So this comes from exit C, and the complementary superposition comes at exit D. So now let's look just at one exit, namely exit C here. So when we look at the expectation value of momentum in Z direction for the electrons that come out at exit C, so this is post-selection, we're using this Gaussian wave function just so we can plot something. And when we look at the expectation value of momentum, we see that there is a region of the parameters delta. Delta is the kick in path B, and T is the transmission coefficient of the first beam splitter. So there's a region of parameters that the average momentum is negative, even though the kick is always positive. So there's this whole range of parameters here that we can get a negative average momentum transferred to the electron. And this is out of the weak interaction regime. The weak interaction regime would be that W here, the width of the wave function, is much larger than delta. And here we have things of the, when the ratio is of the order of unity. So this is out of the weak interaction regime. And what is behind this effect is an interference effect. So if we look at the original wave function that comes through path A, so here it's centered on 0, and this is the wave function from path B, which suffered the force. So it's a positive force. The thing here is that when we have this phase causing a destructive interference, we're going to have this large amplitude here from the red wave function subtracting more from the positive part of the blue wave function than from the negative part, such that in the end, the resulting wave function, which is the subtraction of the two, will have more amplitude in the negative side than on the positive side. So this is an destructive interference effect. And one question that we can make is, how is momentum conserved here? Because we're doing nothing, we superpose this with a positive force, and in the end we have a negative momentum transfer. But we have to remember that we're doing post-selection, and there is a low detection probability for these events. So here is the plot of the probability of detecting the electron in exit C for the same parameters here, the kick and the transmission coefficient of the beam splitter. So we see that whenever the average momentum transfer is negative, the probability detection is very low. And this is connected to the fact that we have destructive interference. And of course, if we go to the other exit and collect the data that we were before trying out, we're going to see that there is always positive momentum transfer in the complementary superposition, such that if we sum the probability of coming out at C with the average momentum transfer at this exit, with the probability at D and the momentum transfer on that exit, this is just the classically expected momentum transfer. It's just Ehrenfest's theorem. So this is equivalent to having the probability of transmission and nothing happening. And here is the original momentum plus the probability of being reflected and receiving the kick. So here's when quantum comes in. So the post-selection is allowing us to rearrange these probabilities of selecting the electron with certain transverse momentum eigenvalues. And we correlate most of the amplitude for positive Z momentum. So here positive Z with the electron coming out at exit D. And we leave the negative values associated with the electron coming out at C. So if we look at the wave function, it always had these negative eigenvalues available for us. We're just superposing these things in a way that what comes out in one of the exits comes mostly from here, and in the other exit comes mostly from here. And this is the quantum interference of force effect, basically. So these are some ways to do this in the lab. These Mach-Zehnder interferometers can be done with electrons. It's been many, many decades that people have been able to do these things. And one way to do is with diffraction gratings. So you can do diffraction with the electron beams and have different paths, and you can act with different electric fields on each path of your Mach-Zehnder. This has been done with atoms, and this could be adapted to an electronic version of these interferometers. Another possibility to do this would be with neutron interferometers. So a few years ago, there's a group that reported application of different constant magnetic fields in each arm of the Mach-Zehnder interferometer. But if this could be adapted to inhomogeneous magnetic fields, this could be used to make Stern-Gerlach force on the neutrons. So you can have different momentum kicks in each arm of the neutron interferometer due to the interaction with the neutron magnetic moment. And also in the magnetic moment reasoning, we could even have this implemented with a Bose-Einstein condensate. So in this case, instead of a free propagation, we would have internal states of the atoms acting as the two paths of the interferometer. So if we start with a state like this, so this is the internal state, these are the external degrees of freedoms, and a radio frequency pulse can act as the first beam splitter, so we have a superposition of the internal degrees of freedom. And there is a way to do this without disturbing the external degrees of freedom. And again, an inhomogeneous magnetic field can make a Stern-Gerlach force. And if we use the fact that different internal degrees of freedom have different magnetic moments, we can have different forces acting on the external degrees of freedom that are correlated with each of the internal degrees of freedom, so that we have the interference of force. And the second radio frequency pulse can act as the second beam splitter, so that here if we look at internal degree of freedom A, we have something analogous to exit C. So if we have this this displacement minus this. If we look at the other exit, we have this plus this thing here. And we can just apply a second magnetic field so that we cancel this thing. And when we look just at the atoms on state A, we have exactly what we had before. So a state with a zero momentum transfer superposed with a state with a non-zero momentum transfer, and you can always have the opposite momentum transfer that you were expecting. So now, have time, I'm going to shift to an upgrade of this setup in which we have two particles in the same interferometer. So in this case, we don't have an external force applied on the particle, but we have the force acting on one particle will be caused by the interaction with the other particle. So imagine that we have two electrons and they are propagating in the same Mach-Zehnder interferometer. And we want these electrons to be distinguishable. We don't want any exchange forces to worry about. And again, we are only worried about vertical degrees of freedom. And we are doing post-selection on both electrons. So what can happen? So there are situations in which the electrons do not interact. When will this happen? When both of them are reflected or both are transmitted. Then we're going to have one coming through path A and the other coming through path B, and the other way around. And in this component, no force will be acting on either of the electrons. They don't feel each other. But if one of them is reflected and the other transmitted, for instance, they both come through path A or they both come through path B, they are going to suffer Coulomb repulsion in the vertical direction here. One goes up and the other goes down. And such that when we mix these things in the second beam splitter and do the post-selection, of course, we can choose the phases here, and we can end up with something like this, which is a component in which they don't feel force at all, and one component in which they feel Coulomb repulsion. And when we look at the momentum distributions, here we consider Gaussian initial momentum distribution again. So here they have zero average momentum. Here because of Coulomb repulsion, let's say the blue electron is pushed to the left and the red to the right. But when we look at the final state momentum distribution, we see that for each electron, the opposite thing happens. So if here, this is what is compatible with repulsion, in the final state, this will be compatible with an attraction between the two electrons. Again, why does it happen? Interference. Now we have a non-separable state, and we have to do a partial trace and look at each electron separately. So if we trace, for instance, electron 2, we have electron 1, and we see that there will be classical terms in the sense that this will give us a probability distribution, this another probability distribution, and each of these with positive coefficients. It's just a statistical mixture. But then we will have interference terms, and these terms will be responsible for the effect. So here is this thing written in the momentum space. So we have one distribution for nothing happening, one distribution due to the Coulomb repulsion, and the interference term. Such that if we plot these things, here we have the classical terms, so the electron is pushed to the left, but the interference terms, they can be negative, such that when we add these things together, the final wave function has more, sorry, this is not a wave function, this is probability distribution, has more amplitude on the opposite side that we would expect. So it is again an interference effect. And the opposite thing, of course, will happen to the other electron. So I'm going to finish. So I showed you that the quantum superposition of a positive force with a null force on a quantum particle can result in a negative momentum transfer to that particle. And we call this thing the quantum interference of force. We also showed that there are ways to do this, to see this effect in the lab with current technology. And the electrons, two electrons, they can effectively attract each other when they propagate through an interferometer, and of course subjected to post-selection due to this effect, quantum interference of force. And these works are published here. I mean, they are pre-printed here, and thank you very much.
Thank you, Raul. Questions? The night was Harian. Oh, isn't my impression, or in your first plot, we have some discontinuity exactly where the probability 0 and
it looks like, but it's not.
Okay, so explain this, please.
I mean, there is actually there is a it is a discontinuity, but I would like to draw, but I can't. But there is a specific set of parameters that you have exactly the same amplitude on one side and the other. So you shift from having positive amplitude to negative amplitude, and it's very quick. I mean, it's nothing really special.
Are you sure?
I guess so. It's just the way that the wave function is so tiny, its amplitude is very, very small, and you have exactly the same integral on one side and on the other. So it cancels out perfectly.
Okay. No more questions?
How, still in the setup there, so you assume that the field is classical, right?
Yes.
So would make any difference if you were assuming kind of quantum field, if you had like entangled state with the field itself?
Entangled state with the field?
Yeah, because now you have like a which path kind of thing.
Yeah,
right?
actually in the Aharonov proposal, it is a quantum field. So if you have one photon, it kicks the mirror and it gets entangled with the mirror. But after you detect the photon, you just look at the mirror. And then you see this whole thing happening to the mirror. You don't care about what the field did.
More questions? Organizers, do you intend to give an announcement? So let us thank people and call the